quantum neuromorphic artificial intelligence platforms. The objective is to cover the following topics. The main objective is to present a sophisticated technology based on an autonomous artificial intelligence vehicle cognitive neuromorphic platform. The mission is to show several technological paradigms intended to illustrate and to explain the relationship between artificial intelligence, deep learning, cognitive neuromorphic architectures, autonomous vehicle controllers, and complex mathematical algorithms with respect to machine learning as it relates to the autonomous vehicle platform. In addition, I will show an actual representation of an autonomous vehicle prototype. Cognitive ability of the nervous system, neurons, dendrites, and synapses, neuromorphic architectures, and deep learning science engineering paradigm. This segment of the presentation will illustrate how to build a deep neural net choosing a number of layers and neurons with deep, densely connected networking strategies. The artificial intelligence multi-layer is composed of input node layers, hidden node layers, and output node layers. They specifically integrate the inputs and feeds the information to the outputs. And you can create with software mathematical algorithms. The human brain is made of the neuron nucleus, the cell body and dendrites, the axon, the telodendria, and synaptic terminals. There are 1 trillion connections. So the idea with artificial intelligence in deep learning and machine learning is to simulate this environment. Computational neuroscience is a branch of neuroscience which employs mathematical models, theoretical analysis, and abstractions of the brain to understand the principles that govern the development, structure, and cognitive abilities of the nervous system. Artificial intelligence forms part of the cognitive engineering science, which is the scientific study of the mind and its processes. It examines the nature, tasks, and function of cognition. These neuromorphic architectures model in silicon the massive parallel way the brain processes information, as billions of neurons and trillions of synapses respond to sensory inputs such as visual and auditory stimuli. Those neurons also change how they connect with each other in response to changing images, sounds, and the like. That is the process we call learning. These architectures, which incorporate brain-inspired models called neural networks, do the same. That is why I have created this neuromorphic architecture / platform. The autonomous vehicle and robotics system, using a navigation algorithm for dynamic of uncertain environments, moving obstacles are supposed to move on typical patterns, which are pre-learned and are represented by Gaussian processes. A prediction function-based algorithm is used to implement robust freeway driving and autonomous vehicles. Prediction engine is built to predict traffic scenarios. A planning framework is used to improve the level of intelligence and driving quality of the autonomous vehicle. A reference planning layer generates kinematically and dynamically feasible paths, assuming no obstacles on the road. Then a behavioral planning layer takes static and dynamic obstacles into account. Other algorithms used include a point-based Markov decision process algorithm is used for robust single-lane autonomous driving behavior control under uncertainties. Autonomous vehicle decision-making is modeled as a Markov decision process, then extended to a QMDP framework. The R&D cloud software solutions supported by an SQL database paradigm takes data and protocol message parser and parameter structure for calculation and statistical analysis in order to provide map views and historical views, as well as to program the path by which the autonomous vehicle will travel. The cloud computing paradigm provides quick access of data and information from internet and web servers via the WPI network so as to provide traffic info, weather visibility, and road conditions. GNSS provides the program pathway. The car of the future is digital and fully connected. The requirements are changing, and it's not enough to just make good cars any longer. We have recreated an ecosystem to integrate artificial intelligence and speech recognition within the autonomous vehicle and robotic controllers. Here, I illustrate a working prototype of a conceptual digital platform integrated and installed. Core Inteltech R&D provides autonomous and robotic digital platform controller solutions. Using onboard sensors, global positioning systems, lasers, radars, cameras, in order to track other vehicles, detect static obstacles, and localize itself relative to the road model. A three-layer planning system combines mission, behavioral, and motion planning to drive in urban environments. This prototype is an alpha test site, and it presents the design and implementation of an autonomous driverless vehicle for populated urban environments. The system explicitly maps the static obstacles, detects and tracks moving obstacles, considers the unobserved areas, provides a motion plan with safety guarantees, and executes it. The autonomous car software solutions and modules. The software can take data from visual cameras, laser scanners, and radar systems, GNSS, sensors, and cloud database units. We use state-of-the-art hardware and software development tools. Our prototypes are developed with sophisticated in-circuit emulators and software simulators. The radio control transmitters and receivers and the telemetry systems are designed in our labs in Miami, USA. The digital reference platform is integrated by mathematical and artificial intelligence algorithms and software models. Markov decision process, Gaussian processes, and motion estimation algorithms are applied and supported. The autonomous system architecture is integrated by a vehicle and robotic controller, a set of software modules, a vision software models, navigation models and algorithms, hardware modules for implementation of gyros, inertial guidance, radar, and GPS. The infrastructure supports communications protocols for wireless, Internet, WPI network, access points, SQL Server database, cloud, object computing. Cloud computing provides access of data and information from Internet and web servers. Programming modules were developed with Python software, consisting of several mathematical algorithms in order to control the servo motors. The code controls movement. The R&D is a three-process development paradigm supported by CAD, CAD, CAM, CAM. These are the patterns generated in software so as to provide a specific solution to your final tasks in Python, programming modules, software, complex mathematical algorithms. The autonomous controller robotics system is supported by accelerometer for determining outside influences, a compass, magnetometer in order to determine direction, navigation, and location. This prototype illustrates proof of concept, and it represents an alpha test model of our first generation autonomous vehicle robot system. Corp Inteltech mission is to provide solutions by applying our technology offerings to product development. The autonomous vehicle and robotics controller is supported by an accelerometer. The intelligent vehicle integrates GNSS technology and external sensors data, object identification, object classification, and algorithm-based decision-making. Illustration of the braking system. The radar system scans the speed of vehicles ahead, and the orientation sensors tracks motion and balance. The processor provides 3D information implementing object identification, motion vector determination, and collision prediction. The autonomous vehicle is supported by a LiDAR system. It is a solid-state LiDAR system that provides a 360-degree high-resolution mapping with short to long range measurement distance with a laser light. It is integrated by an optical front end, a signal conditioning, an analog to digital conversion, a control and synchronization with external light source. Signal processing is provided for distance output and an ASIL-B safety element. The light detection and ranging system is an active form of remote sensing, measuring distance to targets, surfaces, using narrow beams of near-infrared light. GPS is an important aspect of the LiDAR system, used to calculate the coordinates of targeted objects. Spatial interpolation is supported. Software is used to classify ground returns. A range of interpolation algorithms convert ground points data into three-dimensional surfaces. Scanning pattern, rotating mirrors, large footprint LiDAR support 5 meters to 25 meters.